Hi everyone, in this video we look at modeling periodic behavior. In the last few videos we looked at how to graph cosine and sine functions and how to graph transformed sine and cosine functions. And we can apply the graphs of those functions to problems that have periodic behavior. So in this question, we're told Jeremy gets on a Ferris wheel at a height of 1.5 meters above the ground. The radius of the Ferris wheel is 15 meters, and it takes 90 seconds to ride from the bottom to the top of the Ferris wheel. So here you can probably imagine why this can be modeled by a periodic function. We have somebody that's on a Ferris wheel. Let me just draw a circle here. And if they get on at the base, and as they go on the ride, they are going kind of in this circular pattern, and their height as a function of time is going to be periodic, because they get to the same height after every revolution. And since the speed of the Ferris wheel presumably is constant in this problem, it takes 90 seconds for their height for them to make a full revolution on the Ferris wheel. So they get height values that repeat every 90 seconds. So that's why this is we can model this scenario using a periodic function. So remember that when you graph periodic functions have they have the following properties. If we model using a sine curve, we have that y is equal to a times the sine of k times x minus d plus c. And the same thing if you were to use a cosine curve, we'd have that the cosine curve has the following parameters. Y is equal to a times the cosine of k times x minus d plus c. So the trick with these problems is really to try to figure out these parameters a, k, d, and c. And to be honest, it doesn't matter what function, whether you use a cosine curve or a sine curve to model the periodic behavior in this question, because the sine curve and the cosine curve are only separated by a phase shift. Their graphs are the same shape, and we looked at that in the last few videos. So here, let's think about what actually let me let's just leave those up there for now. Let's think about how I can start filling in some of these parameters here. So first off, I know that my amplitude is equal to the maximum of the periodic function minus the minimum divided by 2. The maximum here is going to be 1.5 plus the diameter, because this, let's say that this, let's sketch this a little bit better. So we've got that this height is 1.5 meters. And the radius is 15 meters. So that means that the maximum height of the Ferris wheel is going to be 15 plus 1.5 plus 15 plus this distance, which is going to be 31.5. So we have 31.5 minus, this would be 1.5, because that's the minimum height, because at the base of the Ferris wheel, Jeremy is going to be at a height of 1.5 meters. So I'll have 31.5 minus 1.5, all divided by 2, which is equal to 15 meters. The next thing to think about is, so this is the amplitude. The next thing that we're going to think about is the c value. The c value is the equation of the axis. So we have that c is going to be equal to the maximum plus the minimum divided by 2. But intuitively, we know that the c value is going to be 16.5 because the c value is the horizontal is the y value of the horizontal line that basically cuts our function in half, and you can see that that's going to be halfway between the maximum and the minimum value. And if the halfway between the maximum and the minimum value is just 16.5, so we've got a height of 16.5, so it would be this height, 16.5 meters. So the c value is going to be 16.5 meters. Now, next thing that we have to determine is the period. So the period, since it takes 90 seconds for Jeremy to ride from the bottom to the top of the Ferris wheel, it's going to take 180 seconds to do a full rotation. So that means that the period is equal to 180 seconds. So now we can figure out what the k value is. Our k value is going to be 360 degrees divided by the period, which is equal to 360 degrees over 180 seconds, which is equal to 2 degrees per second. So that's our k value. The last thing that we need to determine is what is our phase shift. So what's the phase shift here? Now, we can model this using either a sine curve or a cosine curve. Remember, because the sine curve and the cosine curve are congruent. They're the same size and shape. They're only separated by a phase shift and a vertical translation, but in this problem they would have the same vertical translation. So the only difference between using a sine and cosine curve is that they're going to be separated by a phase shift. So let's think about whether it's easiest to use a cosine curve or a sine curve. So if we think about this, at time t equals 0, Jeremy is going to be at a minimum. Okay? So let's actually, maybe we'll start, maybe we'll sketch a cycle of the graph before we figure out what the phase shift is here, just to sort of conceptualize this. So let's sketch out a cycle of this graph. So this is going to be our height as a function of time. This will be time, and this is in meters, and this will be in seconds. Okay, so if we think about this, one cycle takes 180 seconds. So 2 cycles, and it asks to sketch 2 cycles of the graph of this function. 2 cycles will take 360 seconds. So if we make this 360 seconds, well, then this would be 180 seconds. This would be 90 seconds. And this would be 270 seconds. We'd have 45 seconds, 135, this would be 225, and this would be 315 seconds. Okay, so the next part of this is we have to scale the vertical axis. Now, on the vertical axis, the maximum is going to be 30. The minimum is going to be will be 1.5. So let's say that this is 30. Our minimum is going to be 1.5. And then maybe here we'll break our axis, and that way we don't have to worry about we don't have to worry about scaling issues here. And then oh, sorry, the maximum height is not 30. The maximum height is actually should be 31.5, because we've got the minimum 1.5 plus 2 radii, which is 1.5 plus 15 plus 15, which is 31.5 meters. So the maximum height is 31.5 meters. Now, when Jeremy starts on this Ferris wheel, he's going to start off at 1.5 meters. And let me just draw the equation of the axis as well. The equation of the axis is going to be halfway in between here. Halfway in between 31.5 and 1.5. Okay, there we go. So, and okay. So Jeremy starts off at t equals 0 at a height of 1.5 meters. After 45 seconds, Jeremy makes a quarter of a rotation around the Ferris wheel. So if we sketch that out on the Ferris wheel that I've got drawn above, Jeremy, and let me use actually a darker color here. On the Ferris wheel that we've drawn above, Jeremy starts here. After 45 seconds, he makes a quarter of a rotation. So he should be at the equation of the axis, which is 16.5 meters. So after 45 seconds, he's at a height of 16.5 meters. So we'll have a point here. And after 90 seconds, he's at the maximum height, which is here. After another 45 seconds, he's made 3/4 of a rotation. So he would be here. So that's after 135 seconds. And then after 90 seconds, Jeremy's back at the bottom of the Ferris wheel where he started, which is here. After 225 seconds, he's made another quarter rotation. And then after 270 seconds, he's made another quarter, he's back at the top of the ride. At 315 seconds, he's back at the equation of the axis. He's back at a height of 16.5 meters. And then after 360 seconds, he's made another full revolution around the Ferris wheel. So now we can go ahead and we can try to draw a smooth curve through all of these key points. And this gives us a pretty good idea of what our function looks like. So that's 2 complete cycles of this function. Now the reason I did that is to try to conceptualize what kind of, whether we're going to use the cosine function or the sine function to graph this. And remember that we can use either function. One might be a little bit easier than the other. So if you recall, remember that the cosine function starts out normally at a maximum and then decreases at the y-axis. Here we've got our function our periodic function starting out at a minimum and increasing. So if we reflect the cosine function about the equation of the axis, if we use a negative a value and we use a cosine function to model this, then we will have no phase shift. So let's do this first using the cosine function, and then I'll show you how to do it with a sine function that has been phase shifted, or with a phase shift. So using the cosine function, we'd have that h of t is equal to minus 15, because we've reflected the cosine function, times the cosine of k, which is k was 2 times t plus the equation of the axis, which was 16.5. So that's our height as a function of time. Now, if we wanted to use the sine function, there would be a phase shift. Recall that the sine function normally starts out at the origin, and we have a point where the sine function starts out increasing. So this point is normally at the origin, and we use this point and not this point because the sine curve normally starts out increasing from the origin rather than decreasing. So if I wanted to use this point and then say that this is a phase shift and a reflection, I could say that it's a phase shift of 135 units to the or seconds to the right, and it has a reflection about the equation of the axis. That's a little bit more work than just using a phase shift of the regular sine curve. So if I wanted to use the sine curve, I would have a phase shift of 45 seconds to the right, and my height as a function of time would be equal to 15 times the sine of 2 times t minus 45 plus 16.5. So this is my height as a function of time if I use a sine curve rather than a cosine curve. Now both of these equations are correct, and it's up to you which equation you want to use to model this situation.